I wish you all the very best for these 2 days of event. Thank you, and thank you very much. And once again, I thank Gollakota sir and all the speakers of this conference. Thank you, sir.
Thank you.
Thank you, sir. Thank you, sir, so much. Thank you for your motivating words. Now, I would like to request Ms. Shreya Reddy, Director, MLR Group of Institution, to address the gathering. Over to you, ma'am.
Good morning, everyone.
Good morning.
Our respected chief guest for today's inaugural session, Dr. Satyanarayana Gollakota Garu, keynote speakers from across the globe, faculty, research scholar, and students. I extend a very warm welcome to all. Every year, on February 16th, Innovation Day is celebrated to create awareness for innovation and motivate people to create enduring products for the future generations. We are meeting just 2 days after to discuss on advanced materials for innovation and sustainability. I feel invention is not an invention that destroys our planet. What best examples I can quote other than plastic? I'm sure every one of you agree with me. The invention of plastic fundamentally changed the way we manufacture, purchase, and use many products. But lately, we realized the plastic waste problem, and now every year, Plastic Bag Free Day is organized. Today, without innovation, sustainability is also not possible. Both are interlinked. I appreciate and congratulate the Department of Science and Humanities for coming out with a very important topic on advanced materials for innovation and sustainability and organizing this international conference. I hope you have a good time and opportunity to connect with the expertise from across the globe. Best wishes from my side. Thank you.
Thank you, ma'am. Thank you so much. I hope we will carry forward with your motivating words to conduct many conferences in this way. Thank you so much, ma'am.
Thank you. Thank you.
So I now request our chief guest, Dr. Satyanarayana Gollakota, who has retired as an outstanding scientist, DRDL. Sir has been directly worked with Dr. APJ Abdul Kalam on all missile projects and on hyperplane design during the year 1982 to 2000. He was also involved in design, development, and test firing of Astra, beyond visual range air-to-air missile, at least 18 firings from ITR Kalasur. He has also contributed a lot to the nation, for which he has been given recognition and awarded the Prime Minister's Scientist of the Year in 2009. And also very recently, he received his Lifetime Achievement Award from DRDL. Sir, I request you to address the gathering.
Thank you. Good morning, everybody. Thank you, Chairman Dr. Reddy Garu and other management members of the esteemed college. I'll give some 4 or 5 practical examples which we have encountered in our developmental activities, which may motivate some of the young faculty members and students of this college and elsewhere. See, when I joined in the year 1977, we started working primarily on a missile called surface-to-surface 45-kilometer range. We found initially that the missile was not, though it was designed for 45 kilometers, we found that it was always falling short of that range by 1 kilometer or about 500 meters. Then we sat down together and tried to analyze and drew some conclusions. Very interesting conclusions were, those days we used to do the design first and then pick the materials. For example, if you are designing an actuator, you are designing a rocket motor casing, you are designing a casing for the onboard computer, you are designing a casing for the inertial system or the seeker, and so on and so forth. You first design the hardware and then select the material for the hardware. Invariably, you found that the material was not the best choice. Then we found that you had to go in for heterogeneous combination of materials for different subsystems and different components. So ultimately we found that we needed innovation in selecting materials for different subsystems and components, not purely based on functional requirements. After a few years, when we started working on the next generation systems, like Prithvi, Agni, Trishul, Akash, so on and so forth, we found that we needed even much lighter materials, which could bring down the overall system significantly much lower than what we had anticipated. The main problem is when you design at the PDR stage, that is the preliminary design stage, let us say you have come to a number 100 kilograms. By the time you finish actual design, cut the material and start making hardware, and you integrate the material, all the subsystems, you find that you are something like 10 plus kgs. Then you go back to the drawing board and keep wondering where you can change the material without getting into problems, so-called problems of galvanic corrosion. That is, if you use heterogeneous materials and if they come into contact, you have different problems altogether. So then we had to look for materials to circumvent all these corrosion problems and compatibility issues. The moment you look for other materials, we had problems of metal forming, measuring, and eventually maintenance once the items go to the armed forces. So at every stage, you found that you had to think before 2 years or 3 years ahead of times and look for materials which are not there, not available at this point of time. So like that, we went next stage. Next problem was the rocket motor casing. Next was the propellant. Next was the LiDAR that comes between the propellant and the rocket motor casing. All these issues were solved in a serial mode, which resulted in much longer development life cycle time. So to cut short this, what we used to do is, initially itself, you think of unconventional materials. For example, we went into composites. Wherever rocket motor casing, we could save a few kilograms. Now today we are talking about electric vehicles run by lithium-ion batteries, electronic packages, etc. Those days we used to work on steel. Eventually we moved on to aluminum, much lighter. And even afterwards we found that even magnesium is much lighter material compared to these two, including the kind of hardness you need, the stiffness, and the mechanical properties you're looking for. Then came the issues of environmental pollution, and then recyclability, and then biodegradability. Some of these metals are basically biodegradable because the moment they get oxidized, they can be easily recycled and reused again, though sometimes the number is limited depending on the type of the material you are choosing. Then when we try to look for clean energy options like solar, wind energy, tidal waves, etc. In fact, strictly speaking, they are not all that green. If you look at solar, for example, though you use silicon or gallium arsenide solar panels, where solar light is converted to electrical energy, you get first direct current, then use an inverter, and then convert into AC. Even these panels, manufacturing these panels itself, you use a lot of acids like sulfuric acid, hydrochloric acid, etc., which are highly toxic. And even the silicon dust, so-called silicon dust, is very toxic. So we started looking at other materials or coatings which reduce the toxicity and eventually merge with the environment. Then we came across these lithium-ion phosphate chemistry, which was studied in detail in the lab, and found that most of these so-called batteries, they are either reusable or single use. Strictly speaking, they are not really producing electricity, but they are only electricity storage systems. The moment the chemically they come into contact, you supply external power, so-called recharging or charging. They hold the electric power for a while, and eventually they need to be recharged once in 6 hours or once in 8 hours, like that. When we came across other applications for packaging electronics and other aerospace components, we found that we could use composites using natural polymer or polymers with natural fiber, like extracted from wood, pulp, etc. These have slightly less strength, but longer life and recyclability and biodegradability. So with all these factors taken into account, today you cannot say or specify a single particular material for a single application for the whole period of time. Every 5 years or 10 years, you got to look at the material, even if the system was not in use, and see if the materials can be appropriately chemically treated so that they become environmentally friendly and degradable. With all these things, we have generated a document, especially for aerospace vehicles, different components, different materials, different life cycles, and the type of treatment they ought to have periodically by inspection. I think I have taken enough time. I'll hand over to the organizers to wish them a great success in this conference, to think innovatively and to look for materials which could be a combination of what has been used earlier along with new materials. Thank you very much. Over to Dr. Sujata ma'am.
Thank you, sir. Everything I feel which we do or design is an art. So today you made us aware the state of the art for design and development. Thank you, sir, for sharing your valuable knowledge and experience with us.
Thank you.
Now I would like to hand over the keynote sessions to our co-convener, Dr. T. Arun Kumar. Sir. Sir, you are not audible. Arun, sir.
Good morning to all of you. Good morning to Professor Golakota sir, Chief Guest of the ICAMIS, and the Management Chairman Marri Lakshman Reddy Garu, and the Secretary Marri Rajshekar Reddy Garu, and our MLR Group Director Sreya Reddy Garu, and our Principal MLR Principal Dr. K. Srinivas Rao Garu, and HOD ma'ams, and I invite all the HODs and all the participants and all the keynote speakers to the International Conference on Advanced Materials for Innovation and Sustainability, organized by the Department of Science and Humanities. Now I will call upon the Dr. Ramaprabhu sir to give it. So, sir, please join us.
Good morning, Dr. Arun Kumar. I cannot share the thing. You have to allow me to share.
You already joined, right, sir?
Yeah, I'm there. Yeah.
Okay. Sir, Dr. Ramaprabhu sir, currently working as a emeritus professor at Alternative Energy and Nanotechnology Laboratory and Nano-Functional Materials Technology Center and Department of Physics, Indian Institute of Technology, Madras. He has received so many fellowships and associateships. He is a fellow of National Academy of Sciences, and he is a fellow of Royal Society of Chemistry, and he is a fellow of Academic Sciences, Chennai. He is also an AVH fellow awarded by the Humboldt Foundation, Germany. He is a DAD fellow given by the Germany. He also received Thomson Reuters Research Excellence India Citation Award in 2015. His research areas includes technology, second batteries, hydrogen fuel cell technology, capacitors, nanofluids, industrial wastewater treatment, CO2 capture and conversion, biology. He has also written a book on graphene, the wonder machine. He also has patents of nearly 49 pages and he has 18 US patents and Indian patents. He developed nearly 10 technologies. He gave 43 PhD students. 7 students are pursuing PhD under his supervision. He completed nearly 70 research projects. Still, crores of researchers undertaken. So, this is all about his short biography of the Professor Dr. Ramadhan. So, thank you for joining us. Thank you for accepting our invitation. Please take over this session.
Yeah, good morning, everyone. Can you see my slides?
Good morning.
Yes, sir. It's visible. The full screen is on, sir. Thank you.
Yeah, you can see the slides, correct?
Yes, sir.
Okay. Thanks a lot. And let me briefly tell, because already we are late with reference to this program. So we'll quickly do what it's not moving. Okay. So I'm going to talk with the reference to the one of the aims of the international conference, how to bridge the gap between academic organizations like IITs, IICs, and other institutions like your institutions, and industries. So that means that how to transfer the knowledge of these researchers to the industry, where we'll cover the nanomaterials, two-dimensional graphene, and then materials for sustainable and clean technologies and functional materials. Since we don't have much time, I'll be talking about the one-dimensional carbon nanotubes and the two-dimensional graphene, how we take up these materials into small scale preparation to large scale preparation, so that we can bridge the gap between the industries and academic institutions. There is some problem. Okay, so is it okay? I cannot go to the slideshow because some issue is there. Dr. Arun Kumar? Hello?
Sir. Tell me, sir.
Is it okay? You can see the slides?
Yes. We can hear, we can see your slides.
Yeah, fine.
Proceed,
So I
sir.
don't go to the slideshow because there is some issue. Okay. So basically we work on energy, biological and environmental applications of different types of these nanomaterials. I told you one-dimensional carbon nanotubes, and then two-dimensional graphene, and then hybrid materials, and then work on the energy related applications, secondary batteries, and then proton exchange membrane fuel cells, and environmental applications like how to capture the carbon dioxide and convert it, and then industrial wastewater purification. And at present, we are also working on this supercapacitor application for the seawater purification. In addition, we are also working on the hydrogen energy technology to store hydrogen in the solid form in materials, as well as to design and develop hydrogen storage devices. Quickly, we'll move on to the carbon-based materials. So all of us know that we have the diamond, which is a three-dimensional material. In addition, we have the graphite. We know the difference between the diamond and the graphite. You have the sp2 hybridization here, you have sp3 hybridization, so properties are entirely different. This is insulating, whereas graphite is highly conducting. So if you can see that graphite, you have the hexagon layers, hexagons of carbon separated by different separated by 0.34 nanometer between the successive layers. If you can peel off only one or two layers, that means that you tend to get the two-dimensional graphene, and roll it. It's like a sheet. If you roll it, then automatically you will get one-dimensional carbon nanotubes, and then press the ends such that you get the zero-dimensional quantum dot, or buckyball we call it. So from the graphite, one can get easily the one-dimensional carbon nanotubes or two-dimensional graphene or zero-dimensional quantum dots. So I'll go to show first how we have taken up the graphene synthesis in a smaller scale to industrial scale. So it's a very simple technique. We call it as a VD technique, catalytic chemical vapor deposition. So you can easily understand that you have the quartz tube and we have the quartz tube boat where we keep the catalyst, and will allow the hydrocarbon, which is acetylene, ethylene, or anything at particular temperature which you have to optimize, and then with the flow rate, one can dissociate the hydrocarbon into carbon and hydrogen. So hydrogen will go out and carbon will get dissolved in the catalyst, and then one can grow either single-walled nanotubes, multi-walled nanotubes, depending on the temperature and the precursor that you use. For example, if you want the single-walled nanotube, one can use methane at high temperature, whereas multi-walled nanotubes, one can use acetylene, ethylene as a carbon source at a lower temperature. The catalyst is iron, cobalt, and nickel. So, go to the slide show more. Okay, so you can see that the furnace where we have the quartz board. Inside you have the quartz tube, different gases, and this is a catalyst, and then before after the experiment, you can see black kind of a powder, and if you take the high resolution microscope images, you can see that they are the multi-walled nanotubes. Can you see that inner diameter, and outer diameter? So they are the multi-walled carbon nanotubes. I'll show you the video later on because of the issue with reference to the computer. Once we have done that, we can use it. You could get only around 1 gram of the carbon nanotubes. Then what we have done is that completely computerized, and then have a bigger quartz tube, and then instead of mass flow meters, instead of flow meters, we have the mass flow controllers, so controlled by the computer. So one can get almost 10 grams of these carbon nanotubes in a single shot, which we have done it in the lab. Now we wanted to scale it up to almost half a kilogram of carbon nanotubes in a single shot. So what we have done is that we have the 7x7 matrix of these quartz tubes. You can see the 7x7 matrix, and you can see 7x7 matrix. Each one will have the kind of one furnace. Entire thing is optimized at the desired temperature, and then you can see the flow tubes, inlet, and then outlets through which hydrogen will come. So afterwards, one can get almost half a kilogram of the carbon nanotubes, because each one will make 10 grams, and then we have the 7x7 matrix so far. So this thing we have actually transferred to JAMI pool. So they have the now ability to make almost half a kilogram of carbon nanotubes. in a single shot. Once we have done that, we have gone to the two-dimensional graphene. So I have mentioned that this is a graphite. So we wanted to get the few layered layers. We want to peel off few layers. But the problem here is that the van der Waals interaction is very strong. So it is not possible for you to do that, except that you can use a Scotch tape technique to get the single layer peel off, but it is very tedious and you cannot get it in large scale. So we want to make the large scale. So what we have done is that we have used Summers technique, where we allow the graphite to interact with the oxidizing agent and acid, so that the separation between them successive layer is increased from 0.34 nanometer to 0.8 nanometer. That means I'm weakening the van der Waals interaction, but the functional groups have been added. Once you have done this, you have the you can exfoliate. That means separate the layers at high temperature, around 200 to 300 degrees centigrade, at a high pressure. So what happens when the pressure is going on increasing, you can see that the exfoliation occurs, and when the pressure is developing between the successive layers, what happens? The exfoliation occurs. So this is called hydrogen exfoliated graphene, and you don't get a single layer, but it contains maybe a few layers, 6 to 7 layers of graphene. But it is possible for you to make in large quantities. You can see that graphene in the wrinkled form, and wrinkled form where one can get the graphene with a different number of layers. I'll show you the video later on. Okay. There's also a different, simplest method of making graphene in large quantities. What you can do is that you can make the graphite oxide. In the previous slide, I've shown that after graphite interacting with the oxidizing agent and acid, one can get this graphite oxide that can be easily exfoliated with the sun energy. Just use converging lens, and one can get the in no time one can do the solar exfoliation. So this is called solar exfoliation. The most interesting thing is that the electrical conductivity, if you measure, then this is a graphite which is having excellent electrical conductivity. You know that almost 10 to the power of 3 Siemens per meter. But this graphite oxide is having a very low electrical conductivity, almost 7 orders less. See, 10 to the power of plus 3 to 10 to the power of minus 4 Siemens per meter. So this material cannot be used for any of these electrical applications. That's, for example, solar cell, supercapacitor, fuel cells, batteries, we cannot use. So we can do the exfoliation such that all the functional groups which are actually reducing the conductivity can be removed, so that one can get the electrical conductivity more or less on par that of pure graphite. But here the specific surface area is very large, therefore one can use a solar graphene. I will come back to the video later on. So if you see the video, then it's easy for you to understand. But the issue is that I cannot go out of this presentation. Now only it works. So a specific surface area, if you measure, you can see that very close to 250 meters square per gram. Single layer graphene is having a specific surface area of 2,300 meters square per gram. So this will contain approximately 7 to 8 layers. So we have done the HRTEM. You can see that it contains almost 6 to 9 layers. So this is 5 nanometer range. So this is the solar exfoliated graphene, and this will be the hydrogen exfoliated. Sorry, this is hydrogen exfoliated graphene, and this is the solar exfoliated graphene. So once we have done it, we have to use it for different applications. So I have taken the example of proton exchange membrane. So this is a very simple technique where you have the anode and cathode separated by a proton exchange membrane. You can, the meaning you can easily understand. Proton exchange membrane, it will exchange, it will allow only the protons to go through here. So hydrogen is given to the anode. So you have the catalyst, platinum decorated on the either carbon nanotube or graphene. So platinum nanoparticles which have been decorated on the graphene or carbon nanotubes has been used at the anode as well as cathode. So what happens here? Hydrogen will be dissociated into hydrogen atoms and then further into protons and electrons, and this conducts only the protons, therefore electrons will go through the external circuit producing electricity. So here electrons and then protons, and then you will give the oxygen here, so that will produce the water. So this is a kind of a thing that one can use it for electric vehicles, so that absolutely there is no pollution. So the chemistry of the fuel cell is that anode side you have the proton and electrons are produced, at the cathode side water is produced, along with of course thermal energy. So we have taken this, you can see that carbon nanotubes and graphene, and top of that we have put these platinum nanoparticles by a simple technique. And here the carbon nanotubes and graphene. So if you go to the each platinum nanoparticles, this will be approximately 5 nanometer. You can see the atomic planes of the platinum. So platinum nanoparticles in the crystalline nature. And once you have done that, what we can do is that we can make the membrane electrode assembly. So this is your anode catalyst, okay, and this is your cathode. And these are these electrodes. In between you will keep the naphion membrane, that is a proton conducting membrane. So make the membrane electrode assembly, and then allow the gas hydrogen from the through the anode side and the oxygen from the cathode side. So you have the graphite plates, and make the single cell, okay, single cell. So all the components are given here: graphite plates, MEA, and then current collectors, and you are the end plates. So once you have done that, then we'll check the performance. So the performance of this commercial catalyst is this is a voltage, and this is a current density, this is the power density. You can see that very close to 300 milliwatt per centimeter square. But what is the performance with reference to our material is that you can see that we will get almost 700 milliwatt per centimeter square, 2.5 times increase with reference to the performance, because of the use of carbon nanotube or graphene as a support material, which are nanomaterials, and then platinum is also almost 5 nanometer crystalline. And once we have done this, so it's a single cell. So we have to go for the bipolar plates at the oxygen, at the hydrogen and oxygen support. So that means that here hydrogen is given, supply is given. On the other side of this flow plate, we have the bipolar plate. There is a flow field that will be the oxygen for the next single cell. Similarly, here oxygen, at the other side you have the hydrogen. So these are the bipolar plates. So I'll show you the bipolar plates. It's almost 17 by 30 centimeter square size. Okay, so anode, cathode, and then of course we need the thermal energy is produced. So we have to have a water plate, a cooling water plate, and these are the end plates, same dimension, and current collector, same dimension. You can see the half a kilowatt fuel cell. We have calculated almost 19 to 20 single cells are needed. So we have fabricated the single cell, and the dimension, you can see this, you can see that almost 30 centimeters by almost 20 centimeters, and this is also 17 centimeters. So this is the 500 watts fuel cell. So 10 cells have been developed, and with the cathode end plate and the anode end plate, which can give the 500 watts. Okay, I'll show you the demonstration. So here you can see that this is the 500 watts fuel cell. So we have connected more than 16 bulbs. Each will be with 50 watts. So when we use this, the power will be supplied from the fuel cell. You can see that all the bulbs can be grown with current of almost 60 amperes can be drawn from this 500 watts fuel cell of 8 volts. Okay, so what I'll do is that I'll quickly come out of this, and then I'll show the video one by one. So this is the synthesis of multi-valve nanotubes. I hope the videos will work out. Can you see the slides?
Yes, sir. We can see your video.
Yes?
Yes, yes, yes.
Okay, fine. Very good. So this is a huge furnace. Okay, almost you can see the mass flow meters, and this is 60 millimeter diameter quartz tube, and almost 1.2 meters quartz tube. Inside we keep the quartz board. I'll show you the quartz board. Can you see the quartz board where only the catalyst is there? Now the temperature is increased to 700 degrees centigrade, and we allowed the argon and precursor. You can see the growth of the carbon nanotubes. 30 minutes we have allowed. Okay. So this is exactly before and after. Before and after, you have seen with your eyes the video, and then we have made the fully automated instrument. Can you see, sir?
Yes, sir.
Okay,
Yes, sir.
fine.
Yes, we can see.
So mass flow meters have been removed, and then mass flow controllers have been given. Sorry, here you can see the mass flow controllers. And everything is computerized. So it's necessary for us to optimize the temperature flow of the precursors, that is the hydrocarbon, so that and the catalyst, of course, in order to get almost 1 gram of the carbon nanotubes. And then I'll come to the hydrogen exfoliated graphene. Look at the conditions. So you can see the quartz, glass tube. Inside we have kept the graphite oxide, and for us to take the video, and it is just heated to 250 degrees centigrade here. It's just on the hot plate, okay, so that slowly the temperature will reach to 200 degrees centigrade, and we'll allow the hydrogen. It's okay. Arun Kumar, you can see,
Yes, yes, Professor. We are able to see.
Dr. Arun Kumar, can you see the video?
Yes, yes, sir. I can see the video. It's working fine.
the exfoliation occurs. It's a very simple technique. Still easiest method to make graphene from the graphite oxide is so this is a graphite oxide. So just doing exfoliation, because you need around 200 degrees centigrade. This is sufficient for you to get the converging lens with temperatures, sun energy directly falling on that. So you can get instantaneously reduction is taking place. You can, if you carefully listen the sound also. Should I skip it? Been done on the terrace of the department. So only the issue here is that everything is manual, so that the place where you don't put your sun energy properly, then graphite oxide is not going to get converted into graphene. And this is a very simplest technology. So everything is in your hand for you to do that. And finally, the proton exchange membrane fuel cell, 0.5 kilowatt fuel cell. We have to show the demonstration. So you can see the 0.5 kilowatt fuel cell, and each one is 50 watts. You can understand by seeing the video. So he's giving the oxygen supply and hydrogen supply. Look at the current and then voltage on the right hand side panels. See, 25 amperes we are drawing current at approximately 8.2 volts. So it's almost 200 watts. 250. $300. It's almost 500 watts. The current, we could go almost to 60 amperes current we can draw. Okay. Thank you very much, Dr. Arun Kumar, and I'd like to thank all my PhD students and project staff, as well as collaborators from Germany, France, Japan, USA, and most importantly, the financial support from many of these funding agencies and then companies like Mahindra, NTPC, Tata Steel, BHEL, US Air Force, and Naval Research of USA, and financial support from IIT Madras. And thank you for listening. Thank you.
Thank you very much, Professor. Thank you for sharing your indigenously developed technologies with the participants. And
your voice is very low, sir.
Okay. Hello, Professor.
Yeah.
Can you hear me?
Yeah. Now it is fine. Yeah. Correct. Yeah.
Thank you, Professor, for accepting our invitation, and thank you for your presentation, and thank you for sparing your valuable time with us. Showing your the technologies developed in the laboratory to extract the large scale graphene using the indigenously developed technologies. Thank you very much, Professor.
Thank you, Mrs.
Okay, let us see anybody is having any questions. We
Yeah.
will
Sure.
take up
Yeah.
one or two couple of questions. Okay,
Okay.
participants, you have any doubts? If there are no doubts, let me thank Professor Ramaprabhu sir for accepting our invitation. Very much thank you, sir.
Thank you very much. Have a nice
Thank you
day
very
to
much.
everyone.
Okay.
Bye bye. Yeah.
Thank you, sir. Thank you very much. Now I request all the participants to join the technical session in respective Google Classrooms. Thank you. Thank you very much.